Okay, well, hello everyone, and welcome to our webinar, Building Applications with Vector Databases. So my name is Akmal Chowdhury, and I'm filling in today for my colleague Matt Brown. I'll be your moderator today. So here at SingleStore, we organize weekly AI webinars, typically 2 per week, demoing data and AI use cases and new tools and technologies. Okay, now, next slide, please, Ayush. Okay, so we tend to post about these regularly. And so here you can see a future session next Wednesday, how to protect data in a FinServ RAG pipeline. This should be really interesting. Come and watch, demo, and discover how Protecto's new solution can empower RBAC. Okay, so that's role-based access control, if you're familiar with database technology, and tokenize data while keeping context in your large language model financial services applications. So if this sounds interesting, RSVP right now, okay? And that link there that you can see in the bottom left and the QR code that you can scan, I will post those into the chat momentarily, okay? As soon as Ayush gets started. I can't multitask like my colleague Matt, but I will get there very shortly, okay? So we hope to see you there. Okay, great. So next slide, please, Ayush. Brilliant, thank you. Okay, so back to today's topic then. So you're welcome to participate in the discussion throughout the session using the Zoom Q&A button at the bottom of the console. And we do at SingleStore have an internal mission statement, and that's try to answer 100% of audience questions, even if that means following up with people afterwards via email, okay? So this has obviously got more and more difficult with the popularity of the webinars, but please make sure you include your name and email address in the question. We won't be answering anonymous questions. So we'd love you to try out today's technology. Anyone who tries it today will be entered for a chance to win brand new AirPod Pro. Simply click the link, okay? And then again, you can see the link and the QR code there. And again, I will post those momentarily into the chat, okay? So you can have access to that as well. So SingleStore has had a free trial for many years, but we've introduced this new free shared tier as well. Literally in about a second, you can provision this, okay? It's shared resources, but you get it very, very fast, okay? And so we'll say a little bit more about that later. Okay, so today's speaker. So Ayush is a computer science graduate and Georgia Tech. And Matt discovered him online. Perhaps discover is the wrong thing to do because Ayush has always been there, okay? So it's not like he was lost. But Matt found Ayush through the sort of presence online, and he's been an awesome presenter for us in terms of covering lots of LLM-related tools and technologies, and some really cool demos as well. So I'm actually going to have a look at some of the stuff he did in the past because I'm evaluating something that I want to do now, and I like to see how he did it before. Okay, and just before handing over, there's just a couple of slides to show you about SingleStore. Okay, normally if you're a regular, you know that I do these. So a couple of words about SingleStore. Well, it is historically a database management system. Okay, go back in time a couple of years, used to be called MemSQL. Okay, that was both the company and the product. Subsequently added columnar storage. Okay, so it was great for OLTP, kept everything in memory, super fast, but then added columnar storage to be able to do analytics, and then developed this kind of unified storage that can handle both types of data, okay, both for OLAP, online analytical processing, and for OLTP. And it does much more than that. Again, next slide, please, Ayush.
Yep.
Great.
Sorry about that.
No. Take your time, sir. There we go. So this one's got a fair bit of animation on it, but essentially what you have at its core, at its heart, is this universal storage. Okay, so look at it like this 30,000 foot view. And then on the left-hand side, we've got a variety of technologies that we can interface with. So things like Apache Kafka, Apache Spark. So you know that the last webinar I did, for example, we covered a little bit on Spark. We've got another Spark session coming up in the near future as well. And we have this pipelines capability. So that's what the animation shows on the left-hand side, is essentially ingesting at scale in parallel into SingleStore. Along the bottom, then, we've got the various cloud providers. Okay, so you can see AWS, Google Cloud, and Microsoft Azure. Um, you can run SingleStore on-prem as well, if you wish. There is a Docker container too, but I think the quickest way is really to follow the link, which I'm going to share in the Q&A. In literally, I mean, a minute of your time or less, you can sign up. And then for the shared free tier, I mean, it's like 1 second to provision, roughly, okay? It might be even faster. I haven't measured it, but it feels like a second. That's a great way to get started immediately. In addition, you do get like $600 worth of credits, which can go a long way, okay, if you manage those resources very carefully. On the right-hand side, you can see that there's a variety of data model types that we can handle. So yes, relational is at its core, but it can do time series, geospatial, JSON. That support has been there for quite some time. Vectors, which has actually been there since 2017, although it's got a lot better in the recent past, okay, with a major announcement earlier this year, which provides a dedicated vector type, as well as things like approximate nearest neighbor in various indexing techniques as well. Okay, lots of cool stuff there. Check it out, and happy to share that with you if we have questions on that as well. And then along the top, as you can see, a variety of ways in terms of tools and technologies and things that we can actually build, things like IoT applications, or if you want to connect with your favorite tools, you know, JDBC, ODBC support. I use Metabase jar file, you know, it's open source, just download it. It's great for building visualizations, but we have this notebook capability as well, which Ayush is going to demo today. And again, I will share the link for that with you very shortly. Okay, so he's very kindly uploaded that onto the SingleStore Labs website, and that will be available through Gallery as well. So it's easy for you to get started with that. And with that, I will bow out now and let Ayush take over from here. And I'll post those links that I promised. They will go into the chat momentarily, and then I'll be monitoring the questions, okay? And I'll do my best to answer those. Anything that we don't get through today, as I said before, we do have a mission statement to answer 100% of the questions. So please do post them, but make sure you don't post anonymously, okay? It is a requirement that we do know who you are in order to get back to you, okay? Great. Thanks very much. And over to you, Ayush.
Awesome. Thank you, Akmal, for that great introduction. Again, hi, everyone. I'm Ayush and a computer science student at Georgia Tech. Welcome to this webinar where we go over vector databases and all their really cool applications. Imagine a world where data isn't just rows and columns, but actual multi-dimensional spaces where each point holds a wealth of information, right? This is the world of vector databases designed to store, index, and retrieve data points that extend beyond the traditional 1 or 2 dimensional schemas that we typically use for our normal databases. And we use these in a realm called vectors. In the conventional databases that most of us are familiar with SQL, data is handled in tables containing numbers, strings. It's quite similar to well-organized spreadsheets, right? But these traditional systems have really served us well for many numerous applications, and building a lot of different systems with these applications. But as we step into the world of AI and generative AI, especially, the limitations of traditional databases kind of become apparent, right? The data that we deal with in embeddings, which are high dimensional vector values that represent semantic meaning of different text, images, or audio, which we'll get into later. This can be really thought as, these are high dimensional feature vectors kind of representing the essence of the data, right? And vector databases are specifically engineered to manage this kind of represented data in a multi-dimensional space. So it enables us to perform operations that are crucial for AI and machine learning applications, like finding the nearest neighbors in a high-dimensional space or efficiently conducting similarity searches. And today we'll explore the architecture that enables vector databases to perform these operations with astonishing speed and accuracy, explore how they work and the capabilities in various fields, from recommending products, detecting fraudulent activity, and even powering retrieval augmented generation. So let's dive in and explore how these work. So vector databases stand apart from due to their sophisticated indexing and search algorithms, which allow them to perform something called similarity searches. These are not your average searches. They're designed specifically to sift through vast data sets to find vectors, essentially in points in a multidimensional space that are most alike, right? So this functionality forms the core of recommendation systems that curate personalized content, whether it be music, news feeds, shopping recommendations. In the realm of image and voice recognition, vector databases empower systems to identify and match patterns with remarkable precision. And they're pivotal in natural language processing and LLMs, helping machines understand and generate human language with nuance and context. So the process starts with a query being transformed into a vector using an embedding model. And embedding model kind of translates this raw content, whether it be text, images, audio, into a vector representation that captures its essential features. Once we have this vector, it's then sent off into a vector database where the similarity search comes alive, right? It matches the query with the closest vectors. And that's kind of the essence of how these vector databases work. Essentially, it's using these, high dimensional vectors to find that represent these, very abstract terms such as language, images in a very high dimensional vector, and then allows us to find similar vectors based on a query. So leveraging vector databases effectively, follows a structured process that is designed to handle complex data types. So Okay, so initially the journey kind of begins with an embedding model, right? And this is a type of machine learning algorithm that translates high dimensional data into vectors of fixed size. And these are often termed embeddings. So these vectors capture the essential properties of the data, whether it be text, images, or sounds, in a form that in a form that a vector database can efficiently process, right? So for example, if you're using textual content, it's going to be converted into vectors that represent semantic meaning. And this means that the conversion enables operations such as similarity searches, which are foundational to systems like recommendation engines or language translation systems, etc. Anything to do with language. You're turning these embedding models kind of turn these, blocks of text into vectors that can be efficiently searched through. So once we obtain these vector embeddings, they're inserted into a vector database. And this is paired with metadata that kind of maintains a link back to the original content, right? So this allows the database to not only understand the content's essence, but also to retrieve the full data details if necessary. So, upon, getting this query, the same embedding model processes the query to convert it into a vector form. So it's using the same exact model that it used to convert all of the other text that's already in the vector database. So it's using the same embedding model. So then the database performs a similarity search against all the index vectors to find its closest matches. This process of matching involves, calculating distance metrics in a vector space using algorithms such as Euclidean distance or cosine similarity, some very popular, techniques to find distances between two vectors in a vector space. So vector databases really excel in these operations due to their ability to navigate and search through high dimensional spaces very efficiently. It makes them indispensable in fields that require quick retrieval of similar items from large data sets. You could use traditional databases, but A, it's not going to be very efficient to search through just text data or image data. And also, it's going to be very difficult to find an exact match. The whole thing about these vector databases is they find the most similar match. And if you're using a SQL query or something with a traditional database, you're typically trying to find an exact match. So this streamlined workflow kind of from the content to query is kind of like what powers these applications with capabilities such as real-time recommendation, instant semantic search, advanced pattern recognition, retrieval augmented generation. We'll definitely go into these topics later, but that's kind of the basis of that. So vector databases kind of fundamentally alter the querying paradigm from exact matches to similarity-based matches that I was talking about, right? So instead of seeking precise value, correspondence as in like traditional databases. Vector database utilize these similarity metrics, right, to determine the vectors closest to the query in the vector space. And that's kind of how it's finding it. It's not using, exact matches, it's using similarity metrics. So the core of these vector database efficiencies is in its similarity search algorithms. And a lot of these vector databases are using something called approximate nearest neighbor algorithms, or ANN. So these algorithms form the backbone of vector databases, and allow them to handle high dimensional data really fast. So they utilize techniques such as hashing, which essentially maps the high dimensional vectors into buckets for faster retrieval. It uses quantization, which simplifies these vectors into, approximate representations to speed up these distance calculations. And the reason why is because I'll show you a little bit later, the vectors that these vectors that these embedding models are generating, have over 1,000 dimensions, right? And it's going to be difficult to have a very fast system that search through 1,000-dimensional vectors, um, because that's not really reasonable, right? If you have like millions of these vectors. So quantization really simplifies these vectors into approximate representations and to really speed up these distance calculations. And graph-based search is also implemented, which connects points in vector space as a graph for optimized traversal throughout this vector space. And these are kind of some of the basic techniques that are used to improve the efficiency in the ANN algorithms. And these methods really collectively enhance the database's capability to return results that are semantically similar to the query rather than syntactically identical. And this advanced functionality enables powerful applications in fields where understanding the context and meaning of data is more significant than the exact data values themselves. So in the operational ecosystem of vector databases, the balance between accuracy and speed is very key, right? So these databases typically deliver approximate results through a series of sophisticated stages, each which are really critical to the system's overall performance. So the first stage is indexing, and this involves organizing the vectors in a way that allows for rapid retrieval. And what this means is the vector databases employ advanced algorithms such as product quantization, locality sensitive hashing, and hierarchical navigable small world, I believe is that what HNSW stands for. And these are some of the algorithms that it uses to really make the retrieval process a lot more fast. So product quantization kind of compresses these high dimensional vectors and splits the space into a Cartesian product of low dimensional subspaces, kind of what I was talking about earlier, turning these 1,000-dimension vectors that these embedding models generate into something a lot smaller that can be processed a lot faster in these similarity searches. LSH kind of uses these hash functions to map similar inputs into the same buckets, which kind of have high probability of being similar matches. And HNSW kind of creates layers in the graph with varying granularity to facilitate efficient navigation throughout the space. So once the vectors are indexed, the querying phase begins, right? And here's where the database compares the query vector transformed by the same embedding process as the index vector, index content, against the data set to identify the nearest neighbors. So the operation exploits the indexing structure to speed up the search. And the final stage kind of in this process is post-processing. And this is where results might be refined or re-ranked according to different similarity measures or constraints to improve the relevance or accuracy of the return results, right? So this can include recalculating distances, applying filters, or really just adjusting the results based on additional criteria. And this allows us to, re-rank the nearest neighbors using like a different similarity measure, for example, to kind of optimize it and fine tune it towards the best possible results that are most similar to what we have. And these are kind of the stages of the vector databases, enabling them to serve as the backbone for applications that require fast and efficient handling of complex high-dimensional data, such as images, text, and sound. So vector databases are engineered to assess similarity through a suite of mathematical measures, right? Each are crucial in determining the proximity of vectors within a high-dimensional space. So these similarity searches are kind of pivotal in comparing a query vector against the spaces stored within the database, right? The vector stored in the database. So there's kind of three, main similarity measures that we have here, and they're pretty popular. I think cosine similarity out of these is the most popular and widely used. So yeah, cosine similarity evaluates the cosine of the angle between the two vectors. And its values range from -1 to 1, where 1 signifies identical orientation regardless of the magnitude. And it makes it highly effective for text analysis, where the orientation of the vector is more important than vector length. Um, and the cosine similarity formula, we'll get into that later as we kind of create our own cosine similarity method in the demo. The Euclidean distance, or also known as the L2 norm, measures the shortest straight line distance between 2 points in a vector space. So this is kind of akin to like how someone might measure distance in the real world. Like you have point A, you have point B, and measure how far away those 2 points are from each other. Similar to Euclidean distance, it's a direct measure of similarity, with smaller distances indicating greater similarity. So if you think about a vector space, if you have a two-dimensional vector space, it's just a Cartesian plane. You have 2 points, and you just apply the distance formula. But then you would have to scale that to like 1,000 dimensional spaces, right? And then the final version is dot product. So dot product is another fundamental operation which multiplies corresponding components of two vectors and sums the results. And it kind of acts as, it kind of acts similarly to cosine similarity, but includes the magnitude of the vectors, and thereby provides a measure of both direction and length. So kind of like the differences again between vector databases and traditional databases is, vector databases really handle vector data. That's the main thing. And these are multi-dimensional arrays representing complex data points. So often in the context of machine learning models, their structure is designed around a multi-dimensional space. And they really support the complexity and nature of the data that they store, right? So they're particularly optimized for AI and machine learning applications, which are areas that require rapid processing and analysis of complex multidimensional data. Again, images, text, videos, these are all insanely big dimensional data. You can't really represent them without, thousands of values. And the search method in vector databases is based on, a similarity search, which looks for the closest data points in the vector database to the query that is being looked for. So in contrast, these traditional databases that we've all been used to manage scalar data, which are discrete singular data points like numbers, strings, which are all arranged in rows and columns within a table. So this traditional relational structure is well suited for transactional data with operations, which involve precise queries and updates. And traditional databases are optimized for transactional data processing, ensuring data integrity, efficient handling of CRUD operations, which include create, read, update, delete. And these search methods, the search method kind of relies on SQL queries a lot of the times, that perform exact matches based on the query data that is provided. And that's kind of the main difference. You're doing exact matches versus, closest points in a vector space. So there's a lot of vector databases out there, but SingleStore DB kind of really distinguishes itself as a vector database by really integrating vector data storage with relational tables. So it accommodates a rich variety of data types that Akmal was talking about a little bit earlier. This hybrid approach allows it to harness the robustness and familiarity of SQL for integrated data operations while also catering to the nuanced needs of vector database and data management. So the architecture of the SingleStore DB facilitates not only just storage of vector data, but also simplifies the access to associated metadata and attributes, making it valuable for applications requiring complex data analyses. By enabling both SQL-based operations on vector data, SQL, and just traditional, operations, SingleStore DB offers the best of both worlds. So the flexibility and multidimensional analysis capabilities of vector databases combined with the structured query efficiency of traditional relation databases is kind of what SingleStore DB kind of provides in this situation. The seamless integration positions of SingleStore DB as a compelling choice for developers and organizations is really a compelling choice, right? Because it requires sophisticated data manipulation and retrieval capabilities, that a lot of these, AI applications can't really sacrifice performance. And, the ease of use provided by conventional SQL queries is really a plus here. And, the result is a powerful tool for those looking to leverage the speed and accuracy of vector databases in areas like real-time analytics, personalized engines, and advanced search functionalities, while still having access to SQL queries, SQL-based operations on vector data. So kind of talking a little bit more about these vector embeddings, I kind of mentioned them a little bit earlier, but vector embeddings are fundamental to modern AI's ability to process and analyze language, right? These are the fundamental numerical representations of that kind of encapsulate the essence of words, phrases, entire documents. And you can have vector embeddings for a lot of different types of data. You can have vector embeddings for text. You can have vector embeddings for images, videos, sound, any type of abstract data that is not really represented numerically. If you want an AI system to be able to understand it, or train a model based on it, you're going to need to, convert these very abstract data types, such as language, images, and audio, into these numerical data types that can be understood by AI systems. And that's where these vector embeddings come in, right? They are, they have high dimensional data so for example, if we're doing language, the high dimensional data of language is kind of distilled into lower dimensional yet richly informative vector space, which is, each dimension captures some aspect of the data's meaning. So for instance, words with similar meanings are often located in close proximity within this vector space, right? This is because embeddings that are desired to capture semantic meaning, enabling systems to recognize that king is to queen as men is to woman, and preserving these relationships in the geometry of the space is very key to these systems and these vector embeddings. So vector embeddings allow you to understand these semantic relationships between words. That's kind of impossible to do with just, basic representations of the words, right? If you have the word queen and king, all you can really look at in that situation is like the letters in the words, the length of the word, the number of vowels, consonants, stuff like that. You can't really get the semantic meaning of what those words are actually representing. And that's where vector embeddings and vector embedding models come into play. So these relationships in the vector space are not just limited to simple word pairs. They extend to complex structures, capturing these nuances of syntax and complex, syntax as well. So, we have these three examples on the bottom. We have the male, female ones with king, queen, man, woman. We have verb tense, walking and walked, swam and swimming, and then we have country capital, right? And all these are representations. If you don't have these vector models, it's very difficult to make these, vector embeddings. It's very difficult to make these comparisons between these two. But since we have these vector representations, which are 1,000 dimensions that represent every aspect of what these words represent semantically, then we can actually get the meaning of, Canada to Ottawa, Spain to Madrid. All these different representations can be a lot more robustly represented and, find the similarities between them. So this transformation of language data into vector embeddings allows AI systems to perform sophisticated tasks such as language translation, sentiment analysis, information retrieval, with remarkable efficiency and accuracy in a lot of cases. And this is because of the vectorized form of the data. These 1,000-dimensional vectors. It's much more amenable to mathematical operations that underlie machine learning algorithms. So these vector embeddings are a powerful tool for turning these vast and complex domain of human language, images, etc., into a format that machines can really understand and act upon efficiently. So kind of just getting into like how these embedding models work, right? We kind of have these vector embeddings, but where do they come from? They come from these embedding models, and embedding models, kind of how they work on the back end is they begin with initialization and assigning each unique value in a vocabulary to a random vector. Right. So for example, if you're doing with the English language, you would take every single word in the English language and give it a random vector. And that's how you initialize this model. And it kind of lays the foundation for further learning. And then the process of contextual learning follows, which is where neural networks consume a vast amounts of text data to understand language patterns. So, these models are they're trained on neural networks that are trained on vast corpuses of data. So they're going to, use newspapers, articles, any like a vast amount of data. And the more data that you have, the better these embedding models are going to be. So for example, there's two kind of main things that it's using here. So the continuous bag of words, CBOW model, kind of predicts the target word based on the surrounding context. So for example, if you have the word dog, for example, it would predict that word based on the surrounding context. So if you have like playing fetch or, dog food or something like that, or any words that relate to dogs, it's able to predict that target word based on that. So that's a model that is commonly used. And then also on the opposite side, you have skipgram model, which predicts the surrounding context given a word. So if you have a word, it's going to predict what words should be around it. And then the next stage is the optimization phase, where the true learning occurs in these neural networks, right? So the model iteratively adjusts the word vectors to minimize a loss function. This is a very common way of training a lot of machine learning models, deep learning models, and often this is like a function of the probability of observing a word given a context or vice versa, right? So gradient descent is the optimization algorithm that typically uses this to is typically used to achieve this by taking a small steps in the direction that reduces the loss. And classic model examples include word2vec, which includes both CBOW and skipgram. GLOVE, which stands for Global Vectors for Word Representation. More advanced models, more recently, are BERT from Google and various OpenAI text embedding models that leverage contextual cues from all around the input sequences and make them adept at understanding the nuances and complexity of languages. And again, these embedding models are really important to building these vector databases, right? The vector databases rely on creating these multidimensional vectors that represent the semantic meaning of these words. And these embedding models is what kind of you use to build out your vector database and to convert your raw text into these multidimensional vectors, which are stored in your vector database. So here's some use cases of vector databases, right? So you have recommender items, right? So if you have a recommendation system, if you want a user to buy a certain product based on their previous buying behavior, you can build out, similar vectors to previous products they have, purchased, right? So if in the past they purchased, a lot of dog food, or dog related products, and then you would want to recommend them more dog related products, right? Similar to what Amazon, a lot of these platforms do. And so a lot of the times you want to, take all the vectors that are represented for all the products they've bought in the past, and then, look based on that system, recommend the closest, using like these ANN, approximates near its neighbor, and similarity searches, kind of getting the closest vectors to that, dog products that we've done in the past. That's kind of an example of recommendation system. So another one is fraud detection by detecting anomalous patterns by comparing, transaction embeddings against known profiles or fraudulent activity. You can use vector embeddings and vector databases for facial feature embeddings to help in security and surveillance for facial detection. And a lot of these facial detection algorithms are one shot, so it just needs to look for in a vector database, just for similar vectors based on the facial embeddings. Help with customer support with similar queries with predetermined or little varied responses. So you can have chatbot systems for your customers to interface with, and you would want to have a vector database to kind of help in that process. And that's kind of where retrieval augmented generation comes in as well, which combines the power of large language models that we're seeing today, such as GPT, Gemini, etc., with a knowledge base of vectors that quickly, that support quick retrieval based on user queries. So for example, retrieval augmented generation, right? You have a user who queries about a recent news event, right? And as we all know, ChatGPT, a lot of these large language models are base models, and they're not trained. They're not. They don't have access to live data. They're trained, 6 months ago, and that's where their news cutoff is. Everything that happened after that 6 months, it has no idea what happened. So if you're trying to make something where that's like a user can query about, news data or something very recent that the large language model does not have access to, or with specific domain requirements, such as like if you're making something for like finance or um, you're making something for medical space, something like that. These large language models are not going to be optimized to do that. And that's where RAG comes in. And just talking a little bit more RAG on this next slide. So just again, some more, just going into these, applications a little bit more. So vector databases can really excel in applications with similarity searches. So they transform the landscape of search functionality with their adeptness in navigating vast data sets to find images or videos based on content resemblance. Again, RAG, which we'll talk about in a little bit, which kind of harnesses vector databases to augment the responses for large language models. So they really improve the relevance and accuracy of outputs in applications like chatbots and automated summarization. And also you can do, again, a little kind of what we're talking about, recommendation systems for vector databases to align user preferences with features within the same vector space. So a little bit of some code examples here of what we were talking about. So enhanced search functionality, right? So content-based retrieval is a method that relies on searching using, content's vector representation rather than a traditional metadata or keywords. And this approach really yields more precise and contextually relevant search results by comparing the content's essence in a multidimensional vector space. So vector databases demonstrate their strength and efficiency at scale, right? So they're really specifically tailored for high speed search. And that's why you can enhance the search functionality instead of finding, these exact matches, you can find a lot of these close similar results. And this efficiency is really achieved through sophisticated indexing and querying of techniques that are optimized for vector data. So here's some code on the bottom of the screen, and you can kind of see what we're looking at here. So we have an example query vector, just four-dimensional vector with this data. And essentially what we're doing here is we're performing a similarity search, this hypothetical similarity search algorithm based on that query vector in a vector database. And essentially, once we get the result, we can find all the results is going to be like all the vectors that is as close as possible to that that vector that we search for in the vector database, and we're going to find we're going to print out every close result that we found, and then figure out, and then it's also going to print out the similarity score that it also generated based on our similarity search model. So again, next we have retrieval augmented generation, which is a very common technique nowadays to where the method, it's kind of where you generate text by a model by actually using data directly from a vector database to kind of give contextual relevance to the user's query, right? So here's generally how these systems work, right? So when they start off with the query formulation, so when tasked with generating a response, RAG formulates a query based on the input it receives. So the query encapsulates the context or the specific information required to generate the accurate response. So the user puts in their query, and using the query, RAG searches the vector database to retrieve relevant documents or data points that are relevant to that specific query. So the vector database, which has indexed information as vectors, allows the efficient and similarity search from that user query, allowing us to quickly fetch content that is semantically similar to the query. And so the next step is the information integration. And this is kind of where, once the relevant information is retrieved, RAG integrates this data, with its pre-trained knowledge to generate a response. So this step is where the actual augmentation happens, where it's retrieve the content enriching response from the vector database, and you have the query. So you kind of combine the two. And if you look at this example code, right, we have the query vector, which is the whatever the question from the user is. So for example, this one is what causes seasons to change. And then it's going to be doing the similarity search similar to what we did earlier, based on that query vector. And the query vector is going to be using this text to vector algorithm or model. And that's, for example, an embedding model, right? You could use any embedding model you want there. It would generate that, the vector, and then essentially the input for the LLM would be the original question that the user asked, um, plus the document, the relevant documents that this similarity search found that are contextually and semantically relevant to whatever the user's question is. That's kind of how it, feeds in. The prompt is now changed from just the question to the question and the relevant context from the vector database. And then that's fed into generative response, which is, then that large language model can generate response based on, the context and the query. And so finally, we have the recommendation systems. And again, a very similar approach where you compare vector representations of user preferences with those of available items. And this allows for highly personalized recommendation systems. And again, you would use the user preference vector, and then you would do a similarity search and find items that are similar to that, with a very high similarity score. Awesome. Okay, now let's get into our code walkthrough. So let me just give me a moment here and I'll share my screen. Okay, cool. Yeah. So here is where let me just move this to the side for 1 second. Here is the notebook for today's webinar. Akmal, have you shared this in the chat for people to? I think it's on the spaces.
Yeah,
From
I'm just going to do that, Ayush. So just as you're getting started, let me drop off the questions for a moment and then post that link in the chat.
Awesome, sounds good. So yeah, so you should be able to access this. It's directly stored in the SingleStore labs in their spaces and notebooks. And once you can open up the notebook and you can also run it directly um, you know, in Colab. So essentially, we're going over, what is in a vector database. These are kind of just similar things, kind of what we talked about in the slides. So vector databases are designed to store and index data points, as known as vectors. But let's get into the code, right? So the first thing is we need to do these required installations. And I already have all those done. So we'll move on to the next thing in this notebook, right? So the first thing we're talking about here is an example of a vector embedding. And this is kind of like a method that I created just for an example. It's not something that you would use in a professional system or any robust system to get these vector embeddings, but it's just an example of how you would it's the essence of what these vector models are doing. Um, so example right here, I'm creating this word to vec function. Essentially what it's doing, it's creating these 5 features. And obviously this is, unrealistic. It's just for example here, and it's a rule-based system instead of a model. But we're using these 5 features. We're using the length of the word, the number of vowels in the word, whether the word starts with a vowel or not, whether the word ends with a vowel or not, and the percentage of consonants in the word. And using those 5 features, I'm creating a embedding model, or embedding, I guess, rule-based system here. So the first thing again is to initialize the vector of 5 dimensions. So the first rule is to get the length of the word, the number of vowel in the words, if the word starts with a vowel or not, if the word ends with a vowel, and the percentage of the consonants in the word. And those are five metrics and features that we have in our vector embedding here. So if we run this, we have this word example, and it's going to create these vector embedding. And this is kind of what a vector embedding looks like on a small scale, right? It's just five features here, but these embedding models are going to have thousands and thousands of features. So you can imagine this being a 1,000-dimensional vector. So if you scroll down here, and yeah, again, just to clarify, right? This is just a simple implementation of a rule-based system, and to demonstrate the essence of what vector embedding models do. They utilize neural networks trained on vast data sets to learn these key features instead of, defining them up front. Um, and so let's talk about a little bit of a vector similarity example here, right? So in this example, I create this cosine similarity function, and kind of explaining how the cosine similarity formula works. So essentially, the cosine similarity is the dot product of the two vectors divided by the product of the vectors' normals or their magnitudes. It's a pretty simple formula, but it's something that powers a lot of these, vector similarity algorithms. So essentially, yeah, we have vector A and we have vector B. So we're calculating the dot product. Then we calculate the norms, the magnitudes of each vector, and then simply just take the dot product and divide it by the product of the norms. And then that would give us a similarity score between 1 and 0. And again, 1 is very similar, and 0 is not similar at all. 1 is a perfect match, actually. 0 is not similar at all. And that's kind of what we're doing here. So we have two words here, example and sample. And we're using the same word to vector algorithm that we kind of defined up here. And again, this is a very rudimentary algorithm that's not very robust at all. Just using these are just about the word structure, not about the semantic meaning. If you kind of understand that, right? Here we're kind of saying how many vowels, how long the word is. That's just telling you like the word structure, kind of like how the word is structured again, not the semantic meaning. So if we have the word example and sample, it's just looking at, the word length of example. Okay, that's, one off of sample. You have consonant A, consonant E. It's looking at that type of stuff. If we were to do something like, um, you know, king and queen, from earlier, right? And the similarity score between sample and example is pretty high because it had, similar amount of consonants, similar amount of vowels, and a similar word length. But if we did king and queen, which would theoretically be pretty high, again, okay, I guess the word length is, but let's try like a bigger word, right? So we have king and throne. Um, so this should be very similar, but it's going down in similarity, even though these are very similar words. If we did, palace, um, this should be very high. In terms of an embedding model, we'll see how much higher this is later on. So yeah, again, these are, this a fundamental problem of these systems is a rule-based embedding because it does not give us a semantic understanding of how these words and sentences are structured. It just gives us, just the structure of the words, which is not what we're looking for. But that's why we have embedding models, right? So in order to generate these semantic understandings of the language and vectors, embedding models are used. So in this example here, I'm using the OpenAI embeddings, and essentially, right, I'm getting my OpenAI key, and I made this method called OpenAI embeddings, essentially just sending a response. It's sending a request to OpenAI API, and essentially we have the input, which is um, I believe this should just be input. There we go. And then we have the response. Yeah, so from here we have with this example golden retriever. And you can see like, this is the embedding that we get. And this is kind of insanely big, right? Compared to what we had earlier, just 5 dimensions. This is over 1,000 dimensions just for one word, right? Or two words, I guess. And that's kind of a reason why you should have good dimensionality reduction techniques during the similarity search, because it's very difficult to search through these 1,000 dimensional vectors. It's not going to be very efficient. But if you're able to use product quantization and these other methods that I was talking about a little bit earlier, to reduce these vectors into something that's a lot more reasonable, then you can have very efficient similarity searches. And here's where I kind of, I go over the process of creating a vector database with SingleStore DB. So essentially, I'm going to be using LangChain to chunk and split the raw text documents, and use the OpenAI embedding models to generate these vector embeddings, right? So the first step is to load in your SingleStore DB URL, and then you're using LangChain here. These are all imported. If you see the installation up here, you should have access to them. LangChain, we're using the character tick splitter, which is essentially going to be chunking these into different documents. So you have this huge text file, which is in this example, we have michaeljackson.txt. All I did for this is I just got the information directly from the Wikipedia page, put it into a text document, and then said that's the document. We loaded it into LangChain, and essentially what we're doing is a text splitter, which sets these chunk size to 2,000 characters per document here. Then we have our generated documents from our raw text document. But again, these are in plain English, right? They're not something that AI models can actually understand yet. So essentially, we have to create these embeddings. So we'd use the OpenAI embeddings model to create that. And then final step is to create a vector database using SingleStore DB. So we have our documents, which are plain English. We have our embeddings, which are the vector representations of those plain English documents that are used for the similarity search. And then we have the table name, which is in SingleStore DB, just call it M Jackson. And then we have a query: how old was Michael Jackson when he died? And then documents is we have this variable called documents, which is essentially vector database.similarity search. And that's built in, super easy to use with LangChain and SingleStore DB, where you can just take your vector database and perform the similarity search, a very big abstraction of what we had a little bit earlier here with cosine similarity. But it's very efficient using ANN, a lot of these product quantization techniques to make this search process a lot more efficient. And so yeah, once we have that search process, we would print out. Then we have our results, right? So docs 0 is essentially going to give us the most relevant response. If we do raw docs 1, it's going to be 1 less relevant, right? So think about it like this: the most relevant response is the document with the highest similarity score to the query. And you can get a list of the highest similarity score matches within this within the vector database using the similarity search. And here's the document that I retrieved from this pretty big text document, right? If we open up this text document here, it's pretty big and has a lot of information about, it's the entire Wikipedia page. And it was able to find the very specific part of the Wikipedia, which is about the death of Michael Jackson. And just it gives the entire document. Again, this is a 2,000 word document or 2,000 character document based on our character text splitter. You can increase that or decrease it based on what you're doing and based on how specific you want to be when you search in this vector database. But that's kind of what we did here. And that's kind of how you do a vector search within a vector database using SingleStore. And like one more application that we want to talk about here is retrieval augmented generation, right? So when you think about what you would use this document for, you could use it for a recommendation system. You can use it for a lot of different things. In this example here, we're going to use this vector search from a user query for retrieval augmented generation, right? So essentially, again, we're using the vector database to query for similar documents to the user's query, and essentially get the similar documents, use that as context in the large language model, and then have a much more contextually relevant response. Right, and let me just paste in my SingleStore DB URL again. And essentially here, right, what we're doing is we'd have this document michaeljackson.txt. And we're doing the similar thing where we're creating these documents, we're creating the embeddings, we create the vector database here, get our OpenAI client, and you can run it directly with LangChain. I'm just using the direct API call for OpenAI right now. But essentially, I have a chat loop here, which takes in the user query as an input from the user. It makes sure it's not like an exit command or anything like that. And then this is where the magic happens. So we do the similarity search of the vector database from the user query. Then we kind of use these documents. So if documents, which is kind of saying that if there are relevant documents that it found, because it could be something where it's like the user said, like, ask something that's completely irrelevant to what the system is, trying to do. And if it doesn't find anything, it's going to say, I cannot find any relevant information. But if it does find the relevant document based on the similarity search, then it's going to take the most relevant document, which is 0, and then it's going to, put that into the large language model. So it's going to, have a system message as a context, which is from here, and it's going to have the user query. And let's just try this out. Okay, so we have this interface here where you can input your questions. So you can say the same thing. What age did Michael Jackson die? So it was able to get the right information. I don't know why I was not able to get it from the text. Let's try a different document here. We also have another example with the Super Bowl. So let's try this um, .txt. And we'll kind of new table called Super Bowl. Um, and let's try that out. In the meanwhile, while this is running, Akmal, do we want to start on live Q&A questions?
Yes, Ayush. So, I've been doing my best to answer as many of these as I could. Okay, so quite a few questions about vector DBs in general, and I think a few issues coming up there in terms of single source capabilities. So I kind of did my best to answer those to the best of my ability. I think let me just go back here. Let's see, there's a couple of questions. See if anything in particular caught my eyes. I think quality of results, the ability to use these vectors, and we talk about embeddings, models, and the actual embeddings themselves in terms of what's generated, the actual numbers, if you like, or the arrays, the one-dimensional arrays that we store. And obviously that depends upon which LLM you're using. And even, if it's from a particular vendor or if it's open source, then there may be multiple models as well. Um, Choosing which one is the right one for the job, I think, again, quite a challenge. I mean, you've worked with a lot of these, haven't you? Any particular thoughts on that? What is there some good sort of rule of thumb or some general sort of advice you can give to people in terms of evaluating these LLMs? What's the best approach that they could kind of follow? Any
Yeah,
thoughts on
yeah, definitely. So there's definitely a lot of different LLMs out there. You have, OpenAI's GPT-4, you have, Gemini. I've used a lot of different models, and first thing you can do to kind of get a, pre-assessment of how well these kind of perform is understanding like their metrics and their evaluation scores from, MMLU, benchmarks. And there's a lot of these open benchmarks out there where you can see the performance of these models against other models, and kind of represents the accuracy score in a lot of different situations for code generation, for mathematics, etc. These are openly available benchmarks that you can look up and figure out. Also, me, Akmal, and a professor at Georgia Tech, we did a presentation a little bit earlier I think a month ago at this point, on evaluating these LLMs using this technology called Lighthouse. And there's a lot of these technologies out there now where you can actually take these LLMs and evaluate them based on the expected result versus the result that it actually gave you based on a certain query. So yeah, getting these, there's a lot of evaluator systems out there, and also you can look at these benchmarks that can kind of compare the performances of these models.
right? I noticed we're almost at the top of the hour. Is there anything else you wanted to show there, Ayush? Did the query come through? Apologies, I wasn't looking there, but
Yeah, so it came through. I was able to. I'm doing it for the Super Bowl now. This is
okay,
really
okay. Is
cool.
it still running?
Yeah, it's still running. I can do any query now. But yeah, this is a good example because the Super Bowl kind of something in American sports that happened, last month, right?
Yeah.
And something where it's like you have these large language models, they're trained every 6 months. So if you're doing anything with like, something that's contextually
Yes,
relevant
yes. It won't know about it. Yeah, it'll have to
about it,
wait.
exactly, with RAG-based systems, it'll definitely know about it.
Okay,
Awesome. Um,
great. Should I go ahead and do the AirPods draw? I think
yeah,
we're almost at the top of the hour. Okay, so meantime, then just a reminder, okay, that we do have on Wednesday the how to protect data in FinServ RAG pipeline. And so that's Protecto's new solution. It can power RBAC, tokenized data, while keeping context in your LLM. So that sounds really interesting. A couple of questions kind of came around this in terms of encryption and data protection as well. So this might be, might be for you. It might be something, if you're interested in this area, have a look at that. And then let's have a look. So AirPods winner. Okay, so Mike McCune, lead data scientist in cyber threat analytics at Nike. Well, congratulations, Mike. So we'll be in touch regarding the AirPods shortly. And then also there's another AirPods draw. Okay, so for anyone who's actually created the account, and I posted the link to Ayush's notebook as well, so you can try that out. So if you do that, SingleStore will do another AirPods draw as well, and we'll get in touch with you about that too. Okay, great. And so thank you very much. So we're a minute over time. So thank you all for participating, wherever you are in the world. We appreciate your time. We know your time is valuable, and hopefully this has been useful for you. And for any questions that we couldn't answer, they will be followed up. As I said before, our mission is to answer 100% of the questions. So we'll get back to you on that. And again, thank you. So look forward to joining you, and probably you'll see Matt Brown in the seat next time you participate rather than seeing me, although I'm down for a couple of webinars in the very near future as a presenter rather than as a moderator. And again, thanks to Ayush for an awesome webinar. So, check out his GitHub repo as well. Just search for him and you'll find there's lots of great stuff that he's done and presented, lots of code that he shared as well. All of this stuff, very easy to install and run, and lots of different use cases too. I mean, that's what's very valuable. I think in this day and age as well, particularly where the technology is going in many different directions, and we're not quite sure, if it's right for us, to try something out and experiment with it and to evaluate it is the best way to learn and get your hands on and test it out. Great. Again, thank you all very much for participating. So I'll end the webinar there now. Great. Thank you, everyone. Bye-bye.